The smart city research area have the great potential to contributing to these missions. So to advance general knowledge and awareness of smart city research, we started lighting presentations on every Tuesday mornings. Today, we are delighted to feature the work from Dr. Zoltan Nagy. Dr. Zoltan is an assistant professor in the Department of Civil Architectural and Environmental Engineering at the University of Texas at Austin. He directs the Intelligent Environments Laboratories since 2016. His research interests are smart buildings and cities, renewable energy systems, control system for zero-emission building operations, machine learning, and artificial intelligence for the built environments. His talk today is titled CityLearn Demand Response Using Multi-Agent Reinforcement Learnings. So without further ado, I will turn the screen to you, Dr. Nagy.
Thank you, Veja. Welcome, everyone. Let me quickly go ahead and share my screen and we can get started. All right, thank you. Thanks for coming. Thanks for attending. Thanks for inviting. I'm Zoltan. I'll be talking about CityLearn, which is one of our recent products. Quick background. I'm in the civil engineering department. Right now, my background is in mechanical engineering with focus on robots. And so the way I came to buildings and infrastructure engineering is through a short stint in the School of Architecture in Zurich, with a 4-year postdoc where we worked on robotic facades and the things you see at the bottom here. And so that made me interested in things like energy management in buildings, controlling buildings, and so once I came to UT, I started building a group build of basically anybody who was interested. It's a very interdisciplinary topic, as you know. A lot of architectural engineers, civil engineers, but also ME, EE, ECE, computer scientists. I have architects in the group. So trying to work on, lots of aspects that involve the built environment and AI or machine learning or anything that's sort of like, connotates smart. This picture is from the before times, and I refuse to update it with Zoom screenshots. So once we get back to normal, I will update this picture again with actual a new photo. Like I said, our research is driven by this question: what is a smart building or smart city? There's not such a cool picture or a funny picture for a smart city, so I'll keep the smart building for a while. But really, the focus on smart, right? Everybody has their own definitions. What that means, and so we try to push ours. In a nutshell, right, what I'm really interested in is two things: human responsive infrastructure, and then within that, so built for humans, but also with humans in mind, and interactive with humans. And with that in mind, we work on theoretical solutions and also demonstrations of cool stuff, and that's really where our work shines, I think, when we pull things from different areas and combine them in a smart way to generate new knowledge. As an overview, like I said, we do a lot of machine learning in general. These words, it's a very, catch-all topic. So I'm usually showing it like this. If you look at machine learning, is it 3 categories of supervised learning, unsupervised learning, reinforcement learning. So we do work in all of these, developing novel algorithms or applications to the built environment. Beyond these, we also do things like IoT developments, data analytics. Right before this presentation started, we chatted quickly about our COVID dashboard that we just released, or we just gather everything we could find on how COVID has impacted, us in the area. And so we just, that's another thing, of dealing with large amounts of data in the infrastructure systems. Today's talk will be on RL, reinforcement learning, in particular this one on the right here on CityLearn. And so I'll start and I'll go through why that's an interesting topic. I won't detail reinforcement learning. If you're interested, the best introduction is this movie, AlphaGo, that you can watch on Netflix, I'm pretty sure. Be prepared. One of my students, I teach this class this spring, and I told my students to watch it, and somebody came back and said it's a very emotional movie, so be prepared. that it's not just nerds. It becomes very emotional at some point when humans start to lose on computers. But the point is, reinforcement learning in a few nutshells is a control application or a control paradigm that borrows a little bit from control theory, a little bit from game theory. And the whole idea is that you have an agent, a control agent that takes, control laws or actions by observing the environment through states, and then the environment itself or the designer guides the agent's actions by providing rewards. And so through this interaction of taking actions for given states and receiving rewards, you can, converge to optimal or, good solutions. And so there's a lot of work in these areas recently because of computational advances. And so we're capitalizing on those and see how they apply in a built environment. If you're not familiar with, RL, one simple way to put it is a poetic way. It's really just trial and error. You do something, you fail, you succeed at a certain task, a subtask, and then you get a reward for that. And that reward reinforces certain connections between the states and the actions. It is worth noting that it is not a new idea. It is at the very core of CS and AI, the way it started back in the 50s, from this quote of Alan Turing. Instead of trying to produce programs to simulate the adult mind, which would be more like a supervised approach, why not try to produce one that simulates the child's mind with the idea that you can grow and learn from experience? And so that's really the philosophical foundation of this RL approach, which we're exploring. And of course, that means that you can adapt to individual situations. And when you think about, buildings, and I mentioned before humans, and things that everybody is a little bit different, every building is a little bit different. And so the approaches that adapt easily are very interesting and suitable for that. So that's kind of like as a background. As an application, so where we're applying this is we're thinking into the future, right? We're seeing a future where things become more and more connected, buildings become more and more having more and more individual energy solutions. Like you can have solar panels now, but in the future you probably have more batteries, you'll have EVs, you'll have smart thermostats, you probably have them already, other smart appliances, batteries, storage in your homes, or larger scale storage. And so all of these things will become interconnected and will need some sort of management. And so what we're looking at is what can we do in terms of like emergent behavior when all of these buildings have their agents? How can they sort of like work with each other without having to rely too much on each other, and how far can they go? The very direct application is some of the part that we experienced a couple of weeks ago, which is if you have too high demand on the grid shuts down. And so what we're trying to do is flatten this demand curve on the grid. We'll see in the examples that I showed you. So basically, you coordinate the energy demand with the goal of reducing the peaks and flatten the curve, and that supports the grid's operation. A quick background on RL and the research in this area. So RL for energy management in different areas. So you can see quite a significant spike in the second half of the 2010s, so to speak. And as a side note, look at this graph that we made. It's missing years in between. I don't know how we managed to publish this, but anyway, so there is quite a spike. This is a review paper, and so there's a big spike in application driven by these new results on reinforcement learning applied to video games mainly. And so a lot of people started to do applications in this area. You see HVAC, you see electric vehicles, which is also driven by recent development there, distributed generation and storage, and then smart appliances a little bit. One of the problems, the problems that people are addressing are all very different. So when we went through this review, we tried to classify them. There's a lot of different areas how the way things are connected. And it was very, very, very challenging to compare them even with each other. Even if you had two separate groups working on, let's say, smart vehicle charging, the way they approach the problem, the assumptions, the algorithms, were completely different and not, comparable, which, makes it hard to do research because you don't know what you build upon. So it's kind of like everybody's doing their own sort of like little cookie or their own little soup, and then you really do not drive the research forward. And so when we started this, we did a little bit the same. We did our own little soup, and then realized that that's not going anywhere. So we took a step back, and we spent quite a lot of time, almost a year and a half or two, to develop an environment, a computational environment that would let us, study this problem and let other people study the problem in a repeatable way, and in a standardized way, so we can benchmark stuff. And so we created this gym environment, which is suitable for RL research, and that's what our colleagues in CS are using, and to benchmark or to pick an environment and then benchmark algorithms against it. And so we set that up, we released it, and so I'll be talking about this, and I'll show you an example in a minute. But the main idea is that now we can simulate different types of buildings with their individual characteristical energy use, with different types of energy systems in there, whether you have PV or you have storage, whether you have some sort of signal from the grid. All of that can be integrated into one, and you can have technically as many buildings as you want. You're limited a little bit by computational availability. But technically, we're looking right now to scale to like a neighborhood, like hundreds of buildings, which will be a bit tricky. So what can it do? Specifically, we're looking at energy storage problem. The energy systems are abstracted out. You don't need to worry about them if you're not wanting to deal with them. And so essentially, what you're trying to do is when you to deal or tell the algorithm when, or teach the agents when to store energy from the grid in your thermal storage tanks, or when to release it from the thermal storage tanks. And this way you can alleviate the energy required from the grid. In the current edition, this is from 2019, we just like literally last week released a new version that has electric batteries, so like Tesla Powerwalls kind of things. And then with that, also the ability to model electric vehicle charging. So right now you could simulate fully electrified buildings as things become more and more important like that in the future. But from a technical perspective, we're simulating the energy storage. All the buildings will maintain their thermal set points. We don't vary those. For two reasons. One, I don't think that's a big leverage, especially not in residential buildings. And two, this way we can guarantee that thermal comfort constraints are satisfied. So you never run into this problem of having to leave people in warmer or too cold environments. So there's a technical and philosophical reason to do that. But and the way we simulate that or try to study it is that every building can start in the same way, and you can run them individually. But then some point they will interact on a larger scale, and we try to see how they interact and how their results are shaped. So here's an example for an experimental microgrid of 9 buildings. The 5 at the bottom are residential multifamily homes. 4 of them have a PV. The others are like commercial buildings, a strip mall, I think a small office, a medium scale office, and then a fast food restaurant or something like that. Roughly the load on the non-residential and the residential buildings is the same. So that's how these came about. So it's half-half. In this particular example, we're looking at climate zone 2A, which is hot and humid. I think it's Louisiana we're running here, but it would be just as good to think about it in local here in Austin. If you're wondering what goes into it, things like month of the day, month of the year, day of the week, hour of the day, the environment, so things like the outdoor temperature, diffuse radiation, direct radiation, some forecast. Just because we have in RL doesn't mean you can't use forecasts. Some parts of your non-shiftable loads, electricity, and then things like dishwasher, things like that, whether you have solar generation or not. And then, of course, the goal is to whether you decrease the charge that you have, so you pull energy from your storage, or you increase it, which means you store energy in it from the grid, right? Again, we don't really know how these buildings are looking. There's no knowledge about that. We initialize agents randomly, and we do not exchange information between the buildings for this particular example. The only way they're linked is through their reward. So basically, we tell them, once you stay what you're doing for the next time step, you get a reward based on the energy use. And without too much detail, there is a component that is specific to the building, and there is a component that is specific to all the buildings. So this is kind of like the only way they communicate through each other indirectly through a signal that's the complete demand. So if you think of it from a neighborhood or a microgrid, you don't really know who uses the energy. All you know is I use this much, and then everybody else got to use this much. And so that's kind of like the combined reward that we're getting. So what do we get from this? So let's see. So here's the typical daily demand in the spring. You see the average, the black, the solid curve, and then the shaded area is like the 25 and 75 percentile for the spring, and the fall data. In the middle is the summer, and on the right hand side is the fall. This is a reference, so there's no control here. So you see what you expect. You have the high peaks in the summer in the afternoon. There's a lot less demand in the winter, and then somewhere in between for the spring and fall. One of our reference controllers, which is, well, what if you did this by hand, is the manually optimized heat pump. And that usually what that means is you charge your energy storage in the morning when it's cheap, when you have a high COP, because it's cooler outside, especially in the summer. And so essentially you see that, and the demand is that you're charging in the morning hours, and then after that you don't pull any more electricity from the grid, and you coast through the day basically, and then in the evening you recharge again if you have to. And so you see that as sort of like your reference controller. What you see roughly with these, and this is optimized. So we ran through a lot of parameters to make sure that this is the best sort of like a good comparison, not just anything that's kind of stupid. But this is what a good controller would do. But you see the peaks are almost the same, and they really didn't remove them. You just shifted them to another place, which is not what you want. And this is a big problem if everybody gets a power wall, and then that power wall is set up to do the exact same thing everywhere. And so that'll be a big problem in the future unless we think about coordinating a little bit. The sooner the more of these are in the market, the earlier that problem will arise. So see, you're just shifting the peak. It is a little lower, but you're really just shifting it. Now, if you add something smart into it, a little bit of a RL, of course, in this case, there are other approaches, but I'm selling you RL today. You see the orange curve, and there's two things that are distinct. One, the peak is a lot smaller. So if you look at the summer peaks, it's almost half, also almost half to this one. And not only that, the whole demand curve is a lot more constant. And that means it's a lot more suitable for, predictable to the grid, because it's almost always the same thing. And so with that, you can plan a lot better, and you don't need to plan for peaker plants that are really only running to cover the peak that you have in the afternoon of the summer. And that's everywhere. Like what are you looking at the spring, summer, winter is a little less of a problem, I would have said 2 months ago, but these days that's a different question. So that's a separate issue, especially in Texas. But in general, that should not be that big of an issue for these. Okay. So with that, this was a very simple example. If you're interested in more, so the example was simple because there was literally no coordination between the buildings. There was no, knowledge transfer whatsoever. At Builds last year, this is in the fall, we modified that a little bit by, trying to say what is the minimum amount of information that the buildings have to share, and how much of that would they need to be able to share to improve on this learning, right? And so if you're interested in that, I will not go into detail. It's technical how you set up the actions. But if you're interested in that, there is a paper. You can watch it on YouTube. Jose's talk is on video. So you can listen to it and see the results. There's some cool videos on that. But the results are even better than the ones that I just showed you. Generally, and I'm winding down on my presentation. So, CityLearn has been pretty cool. In order to remember when I started this, I said there's no environment for people to study it. So when we developed it, obviously nobody's going to just use it just because we say so. But what we did is try to make it a little bit more exciting. So we started this challenge last year to get people to use it. We had some nice results. We're currently organizing a special issue based on those papers that came out. We also last week started the new one, CityLearn Challenge 2021. This year we have money to give out thanks to the Energy Institute, the Machine Learning Lab, and also the RASA Institute at CU Boulder that gave us money to be able to provide prize money. And so there will be about $3,000 this year that you can win in different categories playing that. Again, it's pretty cool to see it. People are using it. People are writing papers with it. So it's very exciting for me. I hope it's continuing like that. If you're interested in this, feel free to download it. We released it open source. The IP people almost, hurt my head when they heard that. But I'm a firm believer that this is the way to push this out, and this is necessary. And so we'd like to be at the forefront of that. And this is why we're doing it. So it's quite exciting. The other thing that's exciting is there's a huge community starting to build around this topic. It's come from two sides. The one is a little bit like us, building engineers, building scientists, architects, trying to use RL as a tool and apply it in energy management, but also in design, like optimization approaches. And then there's the other topic, the other colleagues from computer science who work on RL and discovering the buildings and the problems of energy management that I just introduced as a very, very interesting topic to work on, an important topic. NeurAPES, the big conference in the fall, has a whole workshop on RL or AI for climate change, and so a lot of the papers there last year were RL papers. So there is a fusion between these two, and so we at BuildSys we organized this workshop with CMU on building these people together. We had like 120 or so people at the peak attending it, and it was really interesting to see different people with different backgrounds coming together to talk about the same problems. And it's kind of like defining also the grand challenges, because people, like I said, it's kind of like do their thing, but as a community, the grand challenges for this problem are not really defined yet, so we're trying to do that. Again, if you're interested, the RLM 21 call will come out soon. It'll be in the fall, November 19th or something, 20th, on BuildSys 21. And maybe in person in Portugal, but for sure online. So we'll see how that works out. And with that, I'm finishing up. If you're interested in more, you can go to our YouTube channel. Look at Jose's Marlisa presentation. There's a lot of like 2-minute short talks on the RLM frameworks that you can see here, where people have uploaded their teaser videos, and then other like PhD defenses that we have are all published here. So you don't need to read papers. With that, thank you, and we can have a discussion. I hope I stick within my time. And yeah, also our GitHub page, a lot of the stuff we do is free to be used. So you can just go in and check it out. Thank you.
Very much. It's a very interesting talk. I will open the floor to see if there's any question from the audience. One quick question is, where do you get your training data set, and is that enough, or do you feel like what's the requirements for the reinforcement learning in terms of the training data set?
Training data?
Yes.
Yeah. So I skipped over that. So what we did here is we simulate the data. So we have energy simulation in the background, and we ensure that the buildings that we use are heterogeneous and the use is not the same. So there's a lot of thought that goes into that, but it is all energy plus simulated data in this case. And then the other question, that's a very good one, is how long do you need to learn a sufficient amount of information so you can work, so you can say you converged. That is an ongoing topic. It's one of those topics that is actually one of them where we compare algorithms. Do you need half a year? Do you need 10 months? Do you need 2 months? And what does it even mean to do that. Like that's an ongoing debate, and it's a philosophical one, and you'll get a different answer from different fields, I think.
Zoltan, this is a Junfeng. I have a quick question. So,
Mhm.
for this simulation agent, what's the resolution level you can achieve? Like, can you simulate the energy consumption at an individual house level or at the individual appliance level? So, and also what's the time stamp? Is every minute or every day or every hour? So that's a I think the one question.
Yeah. Right. So, I mean, so RL itself, there's works of people who do, you know, equipment scheduling, and they do it on like, you know, minute by minute basis. I think ORNL did some great work on that. Our work is on hourly. So the CityLearn environment works on hourly simulation, and we're only interested in the whole building's energy demand or electricity demand. So there's no like, you know, we're not doing scheduling of the appliances. We do it beforehand. So every building, you know, if you had like a residential neighborhood, the energy use of the, like, let's say the thermostat settings, the scheduling of the dishwasher and the washing machine would be all randomized or you know, stochastic, so it would not be all the same. But beyond that, essentially, we're only interested in the overall electricity demand of the building, and then that's what goes into scheduling whether you're pulling electricity from the storage or not. So I don't know if I answered the question, but it's hourly, basically. It's hourly.
Yeah. Yes.
Thanks. I think there's no more questions. I want to thank you again for your time to give us talk. It's very interesting. We will post the videos and maybe the slides on our website as well. I put our website URL in the chat, and please feel free to visit it there, and you can join our mailing list, and you can follow us on the social medias. And we have events for every Tuesday, so you can check out our next week's events, which is actually related to the building energies and from Pecan Street. That I think we can wrap up for today's session. Thank you for everyone for joining us.